Imagine stepping onto a battlefield where the combatants are masters of chemical warfare, possess skeletons of glass, and can regrow their entire bodies from a single severed arm. This isn't science fiction. This is the reality waiting for you in the few square inches of a tide pool on a rocky shoreline at low tide. We often stroll past these glistening puddles, these accidental aquariums wedged between barnacle-crusted rocks, seeing them as mere decoration on the coastal canvas. But I'm here to tell you the perspective is a profound mistake. What you are actually looking at is one of the most extreme, volatile, and ruthlessly competitive environments on planet Earth. It's a universe in miniature, a lesson in survival etched in salt, and sculpted by the relentless metronome of the moon. To understand a tide pool is to understand the very fundamentals of life itself: adaptation, predation, symbiosis, and the sheer tenacity required to exist in a world that literally tries to kill you twice a day. The rocky shoreline is not a gentle habitat. It's a vertical desert, a marine cliff face where the primary struggle isn't just finding food or a mate, but simply not drying into a crisp, not being smashed into pulp by oceanic force, and not being boiled or frozen alive as the sun and wind wage their daily war. The creatures that call this place home are not the casual visitors. They are the ultimate specialists, the elite forces of the intertidal zone, each possessing a suite of superpowers that would make any comic book hero green with envy. Let's start with the most fundamental, brutal fact of life here: the tide. The gravitational pull of the moon and sun creates a rhythmic flooding and draining that dictates every single action, every evolutionary trait, every moment of life and death. For roughly 6 hours, the ocean advances, submerging the rocky realm in a blanket of cold, oxygen-rich, nutrient-bearing seawater. Life breathes easy. Filter feeders like mussels and barnacles throw open their doors, frantically siphoning plankton from the water. Predatory sea stars glide on their hydraulic tube feet, hunting. Fish forage in the suddenly accessible nooks. Then the cycle reverses. For the next 6 hours, the ocean retreats, abandoning its residents to the air. This is the crisis point. The sheltered water left behind in depressions becomes the tide pool, a lifeboat, but a perilous one. Its conditions are no longer stable like the open ocean. The sun beats down, relentlessly heating the small volume of water. Evaporation accelerates, causing the salinity, the salt concentration, to skyrocket. A gentle rain, however, can have the opposite effect, flooding the pool with fresh water and causing salinity to plummet. Shocking systems evolve for salt water. At night, the same pool can lose heat rapidly, nearing freezing. This is the daily roller coaster, thermal shock, osmotic shock, and the constant threat of desiccation, of drying out. So, how do you build a body to withstand this? The residents have answers that will blow your mind. Let's talk about architecture first. Look at the barnacles. Those white, conical bumps covering the rocks like a layer of stubborn cement. They seem inert, almost geological. But inside that fortress, a shrimp-like creature lies on its back, kicking its legs out through a trapdoor to comb food from the water during high tide. Their superpower? The strongest natural adhesive known to science. Their cement, a complex protein, binds them permanently to the rock, resisting pressures of up to 70 pounds per square inch. They are literally glued to survival. Then the mussels, with their blue-black shells clustered in velvety beds. They use a different strategy: abyssal thread, a flexible, proteinaceous beard that tethers them like guy ropes. This thread possesses a miraculous property. It's both stiff and elastic, with a tip that adheres underwater through a combination of chemical and mechanical adhesion. Feet human engineers still strive to replicate for underwater repairs. But adhesion is only half the battle. Once the water recedes, the great seal begins. The barnacle shuts its opercular plates, trapping a bit of moisture inside its calcified castle. The mussel clamps its two shells shut with incredible force, thanks to an internal hinge ligament and adductor muscles, creating a sealed, humid microclimate within. They are, in essence, living survival pods. But the tide pool is more than just a collection of sealed boxes waiting for the sea's return. It's a vibrant, active community. The most charismatic engineer here is often the sea star or starfish. Watch one move. It doesn't have a central brain or even blood. Instead, it has a hydraulic system. Seawater is pumped into its tube feet, each ending in a tiny suction cup, allowing it to exert a steady, relentless pulling force. This is the tool it uses to prey upon those sealed fortresses, like mussels. A sea star will arch its body over a mussel, attaching its hundreds of tube feet to both shells. Then it begins a slow, patient tug of war. It doesn't get tired. Its hydraulic system can maintain a constant, low-level pull for hours, even days, until the muscles' adductor muscles fatigue. Once a microscopic gap appears, the sea star does something horrifying and brilliant. It vomits its stomach out of its own mouth and through the gap. It digests the mussel inside its own shell, turning the bivalve's fortress into its own soup kitchen before retracting its stomach and leaving an empty shell behind. This is the arms race in action, the ultimate defense versus the ultimate sustained offense. And we haven't even descended into the deeper, weirder pools where the biodiversity explodes. Here, in slightly more stable reservoirs, you find the anemones looking like undersea flower, but are in fact predatory animals more closely related to jellyfish. Their tentacles are armed with microscopic harpoons called nematocysts, which fire upon contact, injecting neurotoxins to paralyze tiny shrimp and fish. Yet within these same stinging tentacles, you'll often see a jewel-like crab scurrying, completely immune. This is the anemone crab, engaged in a symbiotic relationship where it gets protection from predators, and in return, it cleans the anemone and may even bring it food scraps. This is the other side of the tide pool coin, not just brutal competition, but intricate partnerships forged in the crucible of shared hardship. Every square inch is a drama, a symbiotic pact, or an evolutionary masterpiece of biochemistry and physics, all playing out in a world measured in centimeters between the tides. To truly grasp the scale of this daily drama, we need to zoom in further past the obvious players and into the micro-kingdoms that form the foundation of this entire ecosystem. If the sea stars and anemones are the lions and tigers of the tide pool, then the algae are the vast, sprawling grasslands and forests, and the grazing creatures upon them are the herds of wildebeest and zebra. But here's the shocking part. This primary production, this creation of biological fuel from sunlight, is happening in a palette of colors you'd never expect, and through biochemical pathways of staggering complexity. The rocks aren't just gray. They are painted with living strokes of ochre, rust, deep purple, emerald, and brown. This is the intertidal biofilm, a microbial skyscraper of cyanobacteria, diatoms, and microalgae, and it's the first and most critical food source for the entire community. But the star players are the macroalgae, the seaweeds. They face the same desiccation problem as the animals, and their solutions are architectural marvels. The thick, rubbery bull kelp or the bladderwrack use internal gel-like substances, alginates, to hold vast amounts of water, acting like living sponges to stay hydrated during low tide. Their surfaces are often slick with mucilage, further reducing water loss. But the most incredible adaptation is their reproduction. Many release their spores precisely during the highest tides of the lunar cycle, ensuring the maximum dispersal by the retreating ocean. They are, in a very real sense, tuned into the cosmic clock. Grazing on this algal landscape are the unsung heroes, the custodians of the tide pool, the snails and limpets. The periwinkle snail, a small dark spiral, might seem unremarkable, but its tongue, called a radula, is a biological marvel. It, a conveyor belt of microscopic, chitinous teeth, thousands of them that scrape the algal film off the rock like a living, hungry piece of sandpaper. They can even secrete acid to soften the rock as surface to access deeper layers. Their shell is their mobile home into which they can fully retract and seal themselves with a hardened door called an operculum, creating their own personal humidity chamber. Then there are the limpets, those humble, hat-shaped mollusks. They are the ultimate homebodies. A limpet does just wander. It crafts a precise, exact match of its shell edge to a specific spot on a specific rocket's home scar. When the tide is out, it clamps down with astonishing force, using muscle power and suction to create a near-perfect seal that locks moisture in and predators out. Studies have measured their tenacity. They can withstand forces equivalent to a human holding a family car. But at night, or when the pool is submerged, it embarks on a slow, meandering journey, sometimes up to a meter a marathon in its world, grazing a circular path, before returning with unerring accuracy to its custom-fitted scar before dawn. This homing instinct is one of the great mysteries of invertebrate biology, likely involving a combination of chemical trails and physical memory of the rock as topography. Now let us talk about the hidden chemists, the organisms that manipulate their very internal chemistry to survive. The tide pool is a masterclass in osmotic regulation, the balance of salts and water within a body. For fish like the tide pool sculpin or the common blenny, trapped in a warming pool, the rising salinity is a death sentence if unchecked. As the water evaporates, their bodies, which are less salty than the surrounding sea, naturally lose water to the environment. To compensate, they actually drink the seawater, a seemingly suicidal act. But then they use specialized cells in their gills to actively pump the excess salt back out into the water, a process that requires immense energy. They are, in effect, running a biological desalination plant inside their own heads. On the flip side, after a rainstorm, they face freshwater flooding, which causes water to rush into their cells. They must then switch strategies, expelling water and conserving salts. This constant physiological switch flipping is exhausting and defines the harsh metabolic tax of tide pool life. But the chemical warfare goes beyond simple salinity. Some sea slugs, nudibranchs that move through the pools like psychedelic ghosts, perform a trick called kleptoplasty. They eat algae or, even more astoundingly, anemones, and they don't just digest them for energy. They steal the prey's functional chloroplasts, the solar panels of the plant cell, and incorporate them into their own bodies. This allows them, an animal, to photosynthesize sunlight for supplemental energy, a phenomenon so bizarre it blurs the very line between plant and animal. Other nudibranchs go a step further. They consume the stinging cells, nematocysts of anemones or jellyfish, but instead of triggering them, they transport them intact through their gut and into the feathery projections on their backs, using the stolen weaponry for their own defense. Imagine eating a porcupine and then having its quills grow out of your own skin for armor. This is the level of biochemical piracy that evolution has concocted here. And we must address the architects of the pools themselves, the geology. The rock type is everything. Soft sandstone erodes quickly, creating smooth basins. Harder granite or basalt fractures into jagged crevices and platforms. The pH of the rock matters too. More acidic rocks can slightly alter the local water chemistry. But the most significant factor is the power of the residents themselves to modify their habitat. This is called bioconstruction. Millions of barnacles and mussels don't just live on the rock. They create a three-dimensional matrix, a living reef that baffles water flow, traps sediment, and creates millions of new microhabitats for worms, tiny crustaceans, and juvenile fish. They are ecosystem engineers building complexity upon which countless other lives depend. Their collective presence actually reduces the physical force of waves on the rock beneath them, a demonstration of how life doesn't just endure the environment, but actively shapes and softens it. This self-reinforcing complexity is why a mature tide pool on a biodiverse rocky shore is infinitely richer and more stable than a new one, a testament to the power of collective life over brute physical forces. The drama of the tide pool isn't confined to a single day. It's a generational saga, a story written in the language of reproduction and larval survival, which is arguably the most perilous chapter of all. For most tide pool creatures, adulthood in a home scar or beneath a clamped shell is the stable part. The true lottery, the cosmic gamble, happens in the open ocean during their earliest microscopic life stages. Consider the common acorn barnacle again. It is, surprisingly, a hermaphrodite, but it cannot fertilize itself. Its world is the few square centimeters around its sealed shell. So, how does it find a mate? It possesses the longest penis relative to body size of any animal in the world. This extraordinary organ can extend several times its body length to reach a neighboring barnacle and deposit sperm. But for species farther apart, or for most other tide pools, life, the strategy is broadcast spawning. On a specific night, often synchronized with the full moon and the highest tides of the spring cycle, an entire shoreline will seemingly dissolve into a cloud of genetic potential. Mussels, anemones, sea stars, and worms will release billions of eggs and sperm directly into the water column in a milky primal bloom. The timing is precise. The high tide maximizes dispersal, and the cover of darkness minimizes predation on the gametes. This is where the numbers game begins, and it is a game of staggering odds. From that moment of release, the larvae are on their own, adrift in the vast, hungry open ocean. They are zooplankton, part of the drifting soup that forms the base of the marine food web. For weeks or even months, these microscopic versions of their parents float, grow, and undergo metamorphic changes. They are eaten in uncountable numbers by filter-feeding fish, by jellies, by even other plankton. They are at the mercy of currents, which can sweep them out to deep water never to return, or deliver them to an inhospitable shore. The mortality rate is estimated at over 99.9%. For every 10,000 larvae released, perhaps one will survive. Their journey is a passive one, dictated by hydrodynamics, but they are not entirely helpless. As they near the end of their planktonic stage, they must perform the most critical act of their lives, settlement. They must choose, as microscopic beings, the exact spot where they will live, and likely die, as adults. This decision is guided by a sophisticated suite of chemical and physical cues. They use their simple nervous systems to taste the water for the chemical signature of a healthy biofilm, or the smell of their own species indicating a successful habitat. They sense the texture of the substrate, the flow of water, and even the angle of light. The moment of settlement is a point of no return. A barnacle larva, called a cyprid, walks on its antennae like a tiny spacewalker, testing the surface. Once it finds the right spot, often a rough surface near other barnacles, but not too crowded, it exudes a drop of its powerful cement from a gland in its head and glues itself forehead first to the rock. It then undergoes a radical metamorphosis, curling its body into the familiar conical shape and secreting its shell plates. A mussel larva, spat, uses its byssal thread to make a temporary attachment, testing the location before committing fully. This selectivity is crucial. Choose a spot too high in the intertidal zone, and you'll desiccate. Choose too low, and you'll face intense competition and predation from more marine species. Choose a bare rock, and you might lack the chemical cues for feeding. Choose a spot already crowded, and you'll be outcompeted for food. It's a life or death real estate decision made by an organism smaller than a grain of sand. This larval connectivity means that the health of a single tide pool is never an isolated issue. That pool is part of a vast network, a larval supply line that can stretch for miles along the coast and out to sea. A healthy offshore population of adults can seed a degraded shoreline kilometers away, given the right currents. Conversely, a pollution event or habitat loss in one area can rob downstream pools of their future residents. This is why marine protected areas and clean water policies have such a profound ripple effect. They protect not just the visible adults, but the invisible larval bank that stalks the entire regional ecosystem. The tiny hermit crab scuttling in your local pool may have been born miles away, surviving a journey of epic proportions to end up in that specific shell. This hidden connectivity humbles our view of these pools as isolated puddles. They are dynamic nodes in a vast, open network of life. Beyond reproduction, the tide pool is a theater for intelligence and behavior that challenges our vertebrate-centric views. The octopus, a rare but formidable visitor to deeper pools, is an invertebrate genius capable of complex problem-solving, tool use, and even personality. But even simpler creatures display remarkable cunning. The decorator crab, for instance, actively camouflages itself by plucking pieces of algae, sponge, and hydroids from its surroundings and attaching them to hooked setae in its carapace, becoming a walking piece of the reef. It doesn't just hide, it becomes its habitat. Scale this intelligence down further. Copepods, tiny crustaceans that flit through the water, like fleas, exhibit escape responses that are among the fastest neural circuits in the animal kingdom, reacting to the hydrodynamic shadow of an approaching predator in milliseconds. Even the humble sea urchin, a spherical pincushion, demonstrates a form of spatial awareness. Studies have shown that they will gradually move into crevices or cover themselves with shells and debris during the day. A behavior not just for camouflage, but also to reduce light exposure, which they seem to find stressful. Every resident, from the brainy octopus to the reflexive copepod, is engaged in a continuous calculation of risk and reward, a behavior dance as intricate as their physical adaptation. If we step back from the biology for a moment and consider the tide pool through the lens of physics and time, its story becomes even grander. This environment is a perfect laboratory for observing fundamental principles of energy transfer, fluid dynamics, and geological change. Each wave that crashes against the shore, laps into a pool, isn't just moving water. It's a delivery vehicle for oxygen, a distributor of heat, a disperser of larvae, and a sculptor of stone. The force of water is immense. A full-bodied wave can exert pressures of several tons per square meter. To withstand this, the streamlined shape of a limpet or a mussel isn't just for looks, it's an aerodynamic, or rather hydrodynamic, design that minimizes drag and reduces the likelihood of being torn away. The rough texture of a barnacle-encrusted rock actually serves a purpose here too. It creates a boundary layer of turbulent water that dissipates energy, protecting the substrate beneath. Life itself is modifying the physics of its environment to survive. But the tide pool is also a historian. It holds records in its very structure. Those bands of color on the rocks, the black zone of cyanobacteria highest up. Then the gray of barnacles, the brown of mussels, the green of algae lower down are not random. They are a visible expression of the vertical zonation of life, a direct result of species differing tolerances to immersion, air exposure. By studying the precise upper and lower limits of a species band, scientists can monitor long-term changes. If the barnacle band starts creeping higher up the shore over decades, it's a potential indicator of climate change specifically, of warming air temperatures that allow them to survive longer periods out of water. The tide pool is a living, breathing data log, and its entries are written in the life and death of its residents. Furthermore, the fossils found in uplifted ancient shorelines tell us that tide pools and their communities have existed in remarkably similar forms for hundreds of millions of years. The basic body plans of snails, bivalves, and arthropods were already perfected, and occupying these niches long before dinosaurs walked the earth. This resilience over deep time is a testament to the effectiveness of their adaptation. However, the modern tide pool now faces novel threats that test this ancient resilience. Climate change is not just about warmer air, it's about ocean acidification, As the ocean absorbs excess atmospheric CO2, it becomes more acidic. This lower pH directly attacks the calcium carbonate that forms the shells of mussels, barnacles, and snails. It's like slowly dissolving the very bricks and mortar of their fortresses. Studies have shown that under predicted future pH levels, larval stages struggle to mineralize their shells at all, and adult shells can begin to corrode. The tide pool of the future could become a ghost town of weakened, pitted shells, unable to protect their occupants. Add to this the scourge of microplastics. These tiny, invisible fragments, often smaller than a grain of rice, now pervade every part of the ocean, including tide pools. Filter feeders like mussels and barnacles, who evolved to siphon microscopic food from the water, cannot distinguish between a nutritious diam and a piece of polyester. They ingest the plastic, which can clog their digestive tracts, leach toxic chemicals, and create a false sense of satiation, leading to starvation. These plastics move up the food chain from the filter feeder to the crab to the sculpin, concentrating toxins along the way. A 2022 study analyzing tide pools along populated coastlines found an average of over 100 microplastic particles per liter of water, a staggering concentration in what should be a pristine nursery. This is a silent, pervasive pollution that undermines the health of the ecosystem at its most fundamental level. Then there are the biological invaders, species transported across oceans in the ballast water of ships or in drifting plastic debris. In many parts of the world, the delicate balance of the tide pool is being upended by aggressive non-native species. The Asian shore crab, for example, has colonized vast stretches of the Atlantic coast of North America, outcompeting native crabs for shelter and food. In the Mediterranean, invasive tropical algae species are smothering native seaweeds. These invaders arrive without their natural predators and diseases, allowing their populations to explode and reshape the community structure that took millennia to establish. The tide pool becomes a battleground not just of natural competition, but of anthropogenic disruption. Yet, amidst these threats, the tide pool also represents our greatest opportunity for connection and education. It is the most accessible wilderness on Earth. You don't need a boat, scuba gear, or special training to explore one. You just need to be curious and tread carefully. This accessibility makes it a powerful portal for fostering ocean literacy. A child turning over a rock and carefully placing it back to find a scuttling crab or a pulsating nudibranch experiences a jolt of wonder that no textbook can provide. They are seeing biodiversity, adaptation, and ecological interdependence firsthand, in real time. This direct experience is the seed of conservation ethics. When people understand that the slimy seaweed is a vital forest, that the icky barnacle is a marvel of adhesion, and that the empty shell is part of a nutrient cycle, their perspective shifts from one of passive observation to one of stewardship. The tide pool, therefore, is not just an ecological entity, it is a crucial classroom for the next generation of scientists, policymakers, and ocean advocates. So where does this leave us as observers, visitors, and stewards of these miraculous microcosms? We've journeyed from the shocking, warlike reality of survival in a tidal pool, through the biochemical superpowers and architectural genius of its residents, into the epic larval odyssey that connects pools across vast distances, and finally to the physical and modern threats they face. The overarching narrative is clear. A tide pool is a monument to life's tenacity, a museum of evolutionary innovation, and a canary in the coal mine for the health of our coastal oceans. It demands not just our wonder, but our respect and our active protection. The call to action is immediate and personal, because the fate of these places is inextricably linked to our daily choices. First and foremost, if you are inspired to explore a tide pool after listening to this, and I truly hope you are, you must adopt the ethic of a gentle guest. Practice leave no trace principles on the rocky shore. This means tread carefully on bare rock or sand, avoiding the living carpets of mussels and barnacles which can be crushed underfoot. If you move a rock to look underneath, always place it back exactly as you found it, gently and in the same orientation. The underside is a shaded, humid refuge for a whole community of organisms. Leaving it exposed is a death sentence for them. Observe animals where they are. Don't pry them off rocks. The incredible adhesion of a limpet or barnacle is a matter of life and death. And prying them off often kills them, even if you place them back. Don't collect anything alive. That hermit crab or shell is part of a functioning ecosystem. Take only photographs, leave only footprints carefully, and keep your curiosity mindful. Your role extends beyond the shoreline. The single greatest threat to these ecosystems is runoff pollution. What goes down your drain, what you put on your lawn, what drips from your car, can all wash into storm drains and flow untreated directly into the coastal zone. Fertilizers cause algal blooms that deplete oxygen when they decompose. Motor oil and heavy metals are toxic to filter feeders. Microplastics from synthetic clothing and degraded litter are the insidious invaders. You can combat this by using phosphate-free, eco-friendly detergents and cleaners, reducing or eliminating pesticide and fertilizer use on your property, properly disposing of motor oil and chemicals, and most importantly, reducing your overall plastic consumption. Choose natural fibers when you can. Use reusable bags and bottles, and support legislation that limits single-use plastics. Remember the muscle filtering that water has no choice in what it ingests. You have a choice in what you put into the watershed. Furthermore, become an advocate for marine protected areas, MPAs. These are not just far-off oceanic reserves, they include critical intertidal habitats. MPAs that restrict harvesting and limit Coastal Development Act ed. Vital nurseries and genetic banks, ensuring a healthy larval supply to replenish both protected and unprotected areas. Support local and national organizations that work to establish, monitor, and enforce these protected zones. Your voice as a constituent matters. Write to your local representatives about the importance of clean water legislation, funding for coastal monitoring, and the establishment of no-take zones in sensitive intertidal regions. Perhaps the most powerful thing you can do is to become a citizen scientist. Your observations have real value. Organizations worldwide run intertidal monitoring programs where volunteers are trained to identify key species and track their populations over time. This long-term data is invaluable for scientists studying the impacts of climate change, acidification, and pollution. By spending a few days a year methodically surveying a marked plot of your local shoreline, you contribute directly to the global understanding of these ecosystems. You go from being a passive viewer to an active participant in the story, helping to document the changes and sound the alarm when something is amiss. This hands-on involvement deepens your connection exponentially and turns knowledge into meaningful action. Finally, share the wonder. Use your voice, your social media, your conversations with friends and family. Post those incredible photos you took without disturbing anything, but go beyond the aesthetic. Tell the story of the barnacle's glue, the sea star's stomach, the limpet's home scar. Explain why that plastic wrapper you picked up on the beach matters. When people understand the hidden drama and fragility within these pools, they are far more likely to care for them. You become a node in a network of awareness, just as the pools are nodes in a network of life. You can inspire the next child who might become the marine biologist who discovers a new solution to ocean acidification, or the policymaker who votes to protect a crucial coastline. In the end, the rocky shoreline at low tide is more than a beautiful landscape. It is a sermon in stone and salt, preaching lessons of resilience, interconnection, and the delicate balance of life. It shows us that survival is not about brute force, but about ingenious adaptation and, often, cooperation. It reminds us that the boundary between land and sea is not a line, but a vibrant, pulsating ribbon of life, sensitive to the slightest changes in our global climate and local habits. It is a world where every crack holds a universe, every drop of water a history, and every creature a masterpiece of evolution. To protect it is to protect a fundamental expression of life's creativity on Earth. So, The next time you have the chance, go to the shore. Sit quietly by a tide pool as the water recedes. Look closer. See the battlefield, the chemical factory, the nursery, the ancient fossil bed, the modern classroom. See it for what it truly is, and then let that knowledge move you to protect it. The adventure of a lifetime is waiting in a puddle at the ocean's edge, and its future is, in no small part, in our hands. If this deep dive into the secret world of tide pools ignited your curiosity, your journey shouldn't end here. I want you to become an active protector of these micro-wildernesses. Start today. The next time you're near a rocky shore, practice mindful observation. Take nothing, leave everything as you found it, and pick up any plastic you see. Then, take it a step further. In the description below, I've linked to resources for responsible tide pooling guidelines, citizen science projects you can join no matter where you live, and organizations dedicated to fighting coastal pollution and establishing marine protected areas. Choose one link, click it, and get involved. Share this video with someone who needs to see this hidden world. Subscribe and hit the bell, because this channel is dedicated to uncovering the profound stories in nature's smallest corners, and we have so much more to explore together. Your awareness is the first step. Your action is the next. Let's protect these incredible pulse points of our planet, one tide pool at a time.